Much of the following explanation is adapted from Nobel Prize-winning physicist Richard Feynman's lecture on physics, his section called Electricity in the Atmosphere. For every meter you go up in the air, the voltage increases by around 100 volts, or we could say around 100 volts per yard. We can draw these voltage increases using what are called equipotential lines. Notice that the ground is negative and the sky is positive with respect to each other. According to Feynman, this extends upward to 50 kilometers, or 31 miles, where the air is very conductive. This is the case in fair weather. In stormy weather, like a thunderstorm, things are quite different, and I won't talk about that here. But if this voltage exists between your head and the ground, why don't you get a shock? The reason is that your body is a good enough electrical conductor that standing on the ground, you're basically a part of the ground. The equipotential lines would look like this. There's still effectively 0 volts between the top of your head and ground. Similar effects happen with trees, buildings, and so on. What about the electric current? A downward electrical current exists and consists of positive ions, molecules or clumps of matter that have a positive charge. These ions are moving slowly toward the ground. The current density from these ions is very small, around 10 microamps or 10 picoamps, crossing each square meter or yard every second. So in any small area, there's not a lot of power. And that's the explanation about atmospheric electricity adapted from Feynman's lectures.
So if you forget everything else I say tonight, the one thing to remember here is that Earth's atmosphere is always electrified. Normally, we just think about charge when there's thunderstorms and lightning around, but it's electrified all the time, and charge is continuously generated. And that's through a process called ionization. So positive and negative charge is created by ionization all the time. And in our atmosphere, there are 2 sources of ionization. The first is from galactic cosmic rays. So these are highly energetic particles from basically outer space, from outside our solar system, and they enter Earth's atmosphere from above. And as they do so, they create a cascade of charged particles right down to the surface. And because they come from outside our solar system, they're modulated by solar activity. So they respond to magnetic fields. The other source of ionization is radioactivity at the Earth's surface. So this is mostly from gamma radiation from the soil.
So, I recently got a drone. Things are going great. And while most people use their drones to capture footage or just for fun, I've been using mine for the past 2 months to capture free energy.
Free energy, Jay? There is no free energy!
Okay, so maybe free is a relative term. You see, directly above our heads is a power source that literally nobody would expect. The atmosphere itself. Specifically, there's a voltage gradient that exists between the Earth and the sky at all times. It can be hijacked for power, and this was my journey to do so. Hey, I'm Jay, and welcome back to Plasma Channel. If this is your type of science, consider subscribing and turning on those notifications. To extract energy from the atmosphere, Indiana here volunteered as tribute. Knowing the setup draws power, we terrorized one final park. This time I plan to test the Franklin Bell and the Corona motor. There's a bit of a wind today. Jordan and I had to find a second park to go to. The wind's gonna blow this around like crazy, so it's gonna be kind of a test of what this little tiny drone can actually put up with while dragging a wire 100 meters, 150 meters up into the sky. So let's do it though. Ow! Woo! Don't kill me! Oh. Peace! Wind is super strong right now. So if you look in the center of the screen right now, you'll notice the basket's being blown almost entirely out of the field of view. That's because the wind is just gusting up there. So, 100 meters. All right, I'm gonna stop at 115 and hold steady. All right, it didn't blow up yet. Oh, by the way, meet the aerial film crew. I just thought this was a cool shot. Oh yeah, I'm getting shocked right now. This time I just used the electroscope as a quick voltage check. Woo! Now that's a few thousand volts right there. All right, let's see if there's enough current to make this Franklin bell work. Oh, dude! Freaking working, buddy! Yeah! It's a really cool process. The aerial wire places a positive charge on this can, which then influences the foil ball to deliver electrons from the grounded can, which is directly connected to Earth. The clouds finally opened up, so I connected up the corona motor. Like before, one side was connected to ground, while the other was attached to the aerial wire. And after just a few seconds, hey, she's spinning! This is just remarkable. It never really spun that fast, but I just sat and enjoyed the miracle. I mean, I quite literally was siphoning energy straight from the atmosphere. This motor was operating off of several kilovolts, which you could actually hear if you stopped the motor and brought your finger near the aerial wire. That's the sound of coronal discharge. Not long after, the wind started picking up, so we packed up. It's honestly the craziest thing, and you know, if you're anything like me, you're gonna wonder, where the hell does all this energy come from? There's no such thing as free energy, right? I'll give you a hint, it has to do with that voltage gradient I mentioned earlier. Well, I think Mehdi says it best.
The voltage gradient between Earth and the sky is fairly linear, starting with 0 at Earth and increasing by around 100 volts per meter. And it can be shown by these equipotential lines representing the voltage gradient. All the conductive objects connected to ground though, like people, trees or buildings, or even this wire the J guy wants to send to the sky, are at 0 volts, which means these equipotential lines will have to curve around them. But these equipotential lines become increasingly more compressed around the grounded object the higher it is. In other words, the intensity of electric fields it experiences increases with height. Now, if sharp electrodes are present beside intense enough electric fields, the air molecules are ionized that suck electrons from ground through the wire into the electrodes into the positive ions of air. So just like that, we can create electric current.
So, since the electrode was at about 115 meters, we should have produced close to 11,000 volts of electricity. Now, in reality, it was about half that because the setup I made is super lossy, but I really don't care. The physics is super cool, and we got repulsion, linear motion, and rotational motion out of energy pulled from the sky. What more do you want? In the end, this is a really exotic power source that we've actually known about for more than a century. German inventors created this sketch of their power generation facility, published in Science and Invention in 1922. You'll notice balloons are used as the method to keep the wires up at height. Maybe we should revisit this ancient concept.
Of a problem that we would like to solve, we have a volumetric charge density contained within a volume V, and the volumetric charge density is rho sub V as usual. And at some point P, we are interested in finding some field quantity, such as the voltage at point P or the electric field at point P. So from what we've just seen, we know that Laplace's equation applies, and if we can solve this equation, given this volumetric charge density, rho sub V, we can find V, and from V we know that we can then find E by going backwards. So this is a challenging problem to solve, or more challenging to solve, because it is again a non-homogeneous differential equation. And it would be easier to solve if the right-hand side were 0. In fact, the right-hand side is 0 in many parts of this problem. If I take this field point, or this observation point, and I move it outside V, so let's say I move it outside of this volume to this point shown here, then actually at that point there is no volumetric charge density. So the right-hand side is 0, and we get the homogeneous equation that we're looking for. So that equation, where the right-hand side is 0, is called Laplace's equation. So it is a special case of Poisson's equation, and it holds everywhere outside the source region. So everywhere outside this volume V, our problem reduces to solving this homogeneous differential equation, and it basically turns into a boundary value problem. It's important to also realize that we can apply the same concept to many other charge distributions, not just volumetric charge distributions. So the same is true in turning Poisson's equation into Laplace's equation if we had a surface charge density, or a line charge density, or even a discrete distribution of point charges, so long as our observation is not coincident with the charge density itself or the point charges in the case of a discrete distribution, we can turn the problem into solving Laplace's equation. And even with a combination of volumetric, surface, line, and discrete charge distributions, we can apply the same concept.